Hello, I'm Robert Letcher, and in this part of the session, I'll be talking to you about PFAS bioaccumulation and persistence in wildlife, and showing you how and to what degree wildlife can be contaminated using selected ecosystems and species as an example, and then showing how that data can feed into assessment and regulatory processes, for example, from an ecological context. So a little bit of a general outline. So basically, the basic question here is, why should we be concerned about wildlife bioaccumulation of PFAS? And of course, we need a plethora of and a variety of data from a research and monitoring standpoint to be able to feed into assessment and management processes and ultimately contribute to decisions on regulation in Canada, but also internationally. So to show that exposure, persistence, and risk of potential effects, I'll talk about a few case studies. For example, where we have a modicum of information that allows us to feed into these regulatory processes, and that is looking at birds from the Great Lakes of North America and also mammals mainly from the Arctic region. And then we'll sum up and have a couple of take-home messages that we could use for discussion. So you already know what PFAS are. PFAS, of course, are a large family of fluorinated chemicals, but there are many subgroups, and the main subgroup that tends to be of concern in wildlife are the terminal acids. You're all familiar with the perfluorosulfonic acids, PFOS, and the perfluorooctanoic acids, PFOA, for example, and also more recently perfluorohexane sulfonate. And of course, these compounds themselves aren't necessarily taken up and accumulated in wildlife through their ecosystems, but also as a function of breakdown and degradation of precursors of these terminal acids. And of course, PFAS come from a variety of sources, basically a heavy input into the technosphere, products of various kinds, textiles, clothing, flame retardants, and so forth. There's pretty much no limit to where these compounds can be found. So obviously many sources. I'll first talk a little bit about a major regulatory process in Canada known as the Chemicals Management Plan, or CMP. It is co-administered by Health Canada and the Federal Department of Environment and Climate Change in Canada. And basically this program has been going on for a better part of a decade and a half. And it really started out exploring a subset of chemicals from Canada's Domestic Substances List, or DSL, where there's about 23,000 chemicals. And the plan was to basically assess at least 4,300 of these substances. And basically the major ones were really were a priority for requiring chemical risk assessment. So you can see over the years, if you go clockwise, that the numbers were whittled out until finally, very recently, and in fact in the last year of the present incarnation of CMP, there's still about 1,700 chemicals to be assessed. But a little caveat here is that this program, CMP, is in the process of being renewed for 5 or 10 years, hopefully longer, but will also include provisions for the study of chemical mixtures and cumulative effects, which we know are important in terms of the risk assessment context. Specifically, PFAS regulatory activities in Canada, as in many other jurisdictions, the focus has been on the C8 chemistry, PFOS, PFOA, and their precursors. But in Canada, regulatory activities have shifted and focused towards much shorter long-chain carboxylic acids and sulfonic acids, and then the much longer chain versions. This is aliphatic chains. So up to 300 PFAS have been identified on Canada's Domestic Substances List of about 23,000 chemicals. And so basically Canada is assessed and managed up to 200 of those PFAS so far. So there's still a number to go, and including these shorter and longer chain PFSAs and PFCAs. So this kind of is a really overview summary of what sort of data has been accumulated, both from all sorts of types of research, academic and monitoring. But we can see here we have a range of physical chemical properties to toxicological effects, And we can see as you kind of move down to the longer chain, we're in a big red zone, and those are the longer chain PFCAs and PFSAs for which there's essentially no data. It's a little better for the shorter chain, but we can see most of the information lies within for PFOA, PFOS, and the established PFAS in terms of connection to the environment. So basically, how does the CMP carry out risk assessments? Well, it's really built on this ecological risk classification approach, or ERC. And what it is it's a gathering process of as much data as possible that falls under hazard profile and exposure profile. And you can see there, this is just a sub-list of all the possible areas where data would be useful to fit into those profiles. But of course, there reaches a point where assessment has to go ahead with data that exists, because obviously data can always be added to that assessment. But this just gives you an idea of what sorts of data are kind of a priority in terms of fitting into that profiling, and then following into classification rules, and then being classified in terms of the actual assessment. This is a little more clear kind of view of the logic flow for the ERC process. And you can see here for a given chemical that you can see this building of the hazard profile and the exposure profile, and also incorporating descriptor nodes such as in chemical or in silico or in vitro and vivo results for a given chemical or group of chemicals, and also the ADME portion, which basically affects the distribution, absorption, metabolism, excretion of a compound. All that combined feeds into this weight of evidence in terms of the classification process. And so basically, any sort of data that can fit into these nodes is useful in helping with the assessment. So some of the examples I wanted to show you that where data has been generated and feeding into programs in Canada, such as the CMP, there's a lot of recent PFAS data for the Great Lakes through the Great Lakes Herring Gull Monitoring Program of Environment and Climate Change Canada, and in collaboration through the IJC and partners in the US. You can see here for the last 40 years or so, we have been collecting the eggs of herring gulls from 15 colonies throughout the Great Lakes, so both the upper and the lower Great Lakes. That's an important distinction, given the upper Great Lakes there's less human activity than there would be in the lower Great Lakes, and lesser in the upper Great Lakes of sources of chemicals like PFAS. So the archive that we've generated has been extremely useful for looking at new chemicals or emerging chemicals of concern, including many of the PFAS, and including, say, 8 or 10 years ago, PFOS and PFOA. So here is some recent data from that work. Again, these are eggs from 2012, 2013, still, 7, 8 years ago, but it really gives you a good snapshot of what the levels look like. We're looking at a wide range of chain lengths of aliphatic, carboxylic, and sulfonic acids. And you can see from the red bars that the perfluorinated sulfonic acids was mainly made up of PFOS. In fact, more than 90% PFOS. You can see those red bars as well, showing much higher levels in the southern Great Lake portion of the basin, and you can see Lake Erie, Lake Ontario, for example, showing very, very large concentrations in the hundreds of parts per billion. And then for the carboxylic acids in blue, we can see here they're not dominated by just one chain length, but really C9 to C13 make up the bulk of the total PFCAs. So this is something to remember, because it is within that range of chain lengths that we find quantifiable and frequently detectable perfluorinated carboxylic acids in wildlife in general. This was one of the first temporal trends in wildlife back in the early part of the 2010s. And this was a retrospective study we did using our herring gull egg archive to look at 20 years of temporal trends for mainly PFOS and a range of PFCAs. You know, the red here, this is PFOS, and you can see that declines were mostly the case up into 2010 for the upper Great Lakes. And you can see from that green dotted line going down, that was about the time of the voluntary phase out by the major producer of C8 PFOS and C8 chemistry, the 3M company. And so there looks like to be a decline. But in the lower Great Lakes, on the right, you can see basically that there really isn't a decrease. The level had been going up until about the early 2000s, but continued to stay pretty much at those hundreds of parts per billion levels. And this is the sum of the PFCAs, and you can see basically for the majority of the colony sites, so all these locations are colony sites for the gulls and their eggs, you can see that levels are pretty much were unchanging or increasing, even despite the voluntary phase out in the early 2000s. Also part of that study, we looked at, for basically probably the first time it had been analyzed for, but this compound called PFEX, which is used as a replacement for PFOS. But you can see, even though it looks largely the same as PFOS, with the exception of the cyclohexyl ring instead of a long chain aliphatic, the levels are much, much lower down on the sub or low parts per billion in the same eggs. And we had concluded this is likely the result of it not being used in great quantities rather than being overly bioaccumulative. So perhaps a source reasoning. And then more recently, looking at the eggs of gulls, not just herring gulls, but other species across Canada, we published this paper looking at even more recent, so up into the middle of the 2010s. And you can see here that levels are, for PFOS, vary considerably depending where you are across Canada, but particularly high, as you would hypothesize, in the highly urbanized areas. So those larger red circles in the maps translate to what you see in terms of levels on the left. What I also point out here is the FEQ value. That's the Federal Environmental Quality Guideline for birds, Environment Canada for PFOS. And that threshold level is about 1900 nanograms per gram wet weight. And you can see the redded horizontal bar that for many of these, for eggs of these gulls, that some of these levels are coming very close to that cutoff, where not that there's going to be effects, but there is basically a higher risk from that exposure, perhaps chronically rather than acute. Now, another study we recently did with state partners in Michigan and also in the US, we looked at a greater number of sites in terms of herring gulls, but we also did a sub-study where we looked at Caspian tern eggs versus herring gull eggs. And this is important because Caspian terns are basically almost a total aquatic fish-eating bird. They occasionally crayfish and insects, whereas herring gulls feed on a similar fish diet, which dominates their consumption. But they're also opportunistic feeders, as we'd all be aware. We see gulls eating trash or human refuse, and that is a conduit for direct exposure at much higher levels, in some cases, for contaminants. So again, we wanted to make that dietary comparison between two fish-eating seabirds. So you can see here that the study, we wanted to have tern eggs and herring gull eggs from the same locations, coincidental locations, and collected at the same time. So in this case, the spring of 2013, 2014. And we have an upper Great Lake area that's at the top of the map, and then we have one down near the lower lakes in a highly contaminated area of Saginaw Bay. So what you see here is the comparison of the PFSA and PFCA composition in the eggs from the two birds from the different sites. And so basically you take the concentration of an individual PFAA divided by the sum concentration of that particular grouping. And you can see on the left, again, mostly PFOS just like we saw in our previous herring gull studies. So a large proportion, almost all of it, is PFAS. But you can see that for the gulls, there is a tendency for higher concentrations. You can see C6 and C10 PFSA. On the right, you see the proportion of PFCAs, and you can see there are some significant differences. Gulls tend to have higher proportions of longer chain PFCAs than do the terns. So this is not levels, this is basically congener composition. So there are differences, and clearly diet has a large imprint in distinguishing those differences. So these are actual levels, and you can see here on the left are PFSAs and on the right are PFCAs, and the means and the error surrounding those medians. And you can see that across the board that it's the common terns that have higher levels than herring gulls. And of course this strongly indicates that it's the more of the fish diet where we're seeing the source of these particular PFAAs in these two species of bird, but particularly in the common tern. And I bring up that FEQG value, so Canadian Federal Environmental Quality Guideline threshold for PFAS in birds of 1900 nanograms per gram wet weight. And you can see that for some of those terns, particularly in Saginaw Bay, you can see that a number of them are going well above that guideline, because you can see that the concentrations are on a log scale. So it looks like greater concern could be put forth for PFAS exposure in common terns relative to, say, herring gulls from the same breeding site locations. So that's a Great Lakes example where we have different species of birds and the exposure to the established bioaccumulative PFAAs. But now let's switch to a much more remote, quote-unquote, environment, and that's the Arctic. And so basically, just to give you some context here, much of what gets to the Arctic is through marine, oceanic, and atmospheric transport. And this is particularly true for PFAS, particularly precursors. Although there is some debate in terms of how relatively important atmospheric versus marine or oceanic transfer is, but both processes are at play. And of course, that deposition in the Arctic ends up making its way into marine and, to a lesser degree, terrestrial food webs. And with climate change and warming and decreased ice, there's actually more human activity in the Arctic. And this also means more sources of compounds like PFAS, for example, from the burning of garbage in local Arctic sources and communities, for example. So a major program, not a risk assessment program, but one in which exposure data is generated, is the Northern Contaminants Program. This is a federal program which carries out much monitoring and research on legacy and new compounds. And of course, PFAS are part of that equation. The NCP is concerned with contaminants that reach the Arctic, as I showed you, via long-range transport. It tends to be a little more selective in that regard. And of course, that cadre of chemicals is expanded upon when possible in terms of the program and budgets. But one of the main pillars of the program is to also identify new emerging contaminants entering the Arctic food chain. And you can see it may be a bit difficult in the upper left. This is just a listing of all the chemicals that are included in NCP monitoring, and with coincidence of monitoring to those compounds regulated under an international convention. That's the Stockholm Convention on POPs, persistent organic pollutants. And of course, that's because a lot of this data, it feeds into that convention, because many of these compounds have either been listed for some time, have been listed recently, or evidence is required to make a decision about listing for regulation in an international context. So again, this is the ultimate international process to obviously put some brakes on some chemicals that are deemed deleterious to the environment. So this is the UNEP Stockholm Convention. All the data that I've talked about so far in terms of the Arctic or the Great Lakes, all these sorts of, in the data I've shown you, the exposure data, is used, and not just by Canada, but by all nations to put forth their case for how a compound should be listed, and that can take many years. And eventually, if they get listed under an annex, then there is some form of regulation. Annex A is destined that the chemical be eliminated, meaning stop usage altogether. And you can see that in the early days, in the mid-2000s, there was the Dirty Dozen, PCBs, and toxaphene, Mirex, other pesticides. And then there was a big listing in 2009. You can see in the timeline there, that's when PFOS had been added under Annex B. And of course, 6 years prior to that, 7 years prior, it had been phased out by 3M. So that was the first PFAS to be added to the Stockholm Convention. And you can see it wasn't until 2019 when PFOA and its salts were also added to the convention under Annex A. And then more recently, we have perfluorohexane sulfonic acid that is at that point. And in fact, in 2021, a decision is going to be made whether it's added to the convention. So this just shows you how limited these compounds are, but it also shows you how few PFAS have reached this state of information science to make and render a decision about whether it's added to the convention. So I wanted to talk about the Arctic a little more in that context in terms of PFAS. This is a review that came out just last year on PFAS in the Arctic. So, and it stemmed from a report, and this is the Arctic Monitoring and Assessment Program. This is a global circumpolar program. But basically, the report and this paper summarize this current state of knowledge for PFAS in the Arctic. And you can see that just looking at, it's very difficult to see the table in the lower left, but we have below that red line, these are all precursors, sulfamides, fluorinated acetic acids and so forth, fluorotelomere alcohol precursors. And you can see that the absence of an X tells you that there's no data. The presence of an X is, at least in some capacity, whether it be air, water, biota, that there's data. But you can see for the PFAS, which are on the top of that table, that many of those, in fact, still do not have a lot of data for biota, particularly the shorter and extreme longer chain versions of the carboxylic acids and the sulfonic acids. So I've done a lot of work over these last decades on polar bears, particularly polar bears from Hudson Bay. So you can see by the map there, the big body of water bordered by Ontario, Quebec, Manitoba, Northwest Territories, or not Northwest Territories, sorry, Nunavut. But what I wanted to emphasize here, you see some legacy compounds. So you see PCBs, you see chloridanes, and you can see that the levels of PFOS, really it's the dominant PFAS in polar bears, similar to what I showed you for birds. PFOS is in the hundreds of parts per billion, but still PCBs are much higher concentration, whether it's in the southern population of bears in Hudson Bay or the western population, distinct subpopulations of bears. And then PFCAs are again present, not as much as PFOS, but are certainly among the major contaminants and target contaminants that we know so far for bears. But what you can see here, just by the bar graph, so you see the years on the x-axis, that there really is high levels have been going on for the better part of a decade or more in both bear populations. So again, falling back on that 2002 phase out and the 2009 addition of PFOS, for example, to the Stockholm Convention, that there really hasn't been much impact. if you view this as a risk management, in terms of seeing how enforcement or change in regulations actually affects the temporal trends of PFAS, and of course, as I mentioned, PFOS and PFCAs. So let's talk about PFOS. This is, as you can see here, this is again, these are polar bears from the early 2000s, and you can see a much broader analysis of PFAS. In fact, we started looking at some of the replacements like PFEX, the shorter chain analogs, but you can see on the very far right, and of course it's exemplified by the scale in the thousands of parts per billion, that PFOS is by far the dominant contaminant. And then you see, but you see very little PFEX. You see a lack of shorter and very longer chain perfluorinated carboxylic acids in the plot on the far left. In fact, you can see polar bears have a dominant C9 or perfluorononane sulfonic or carboxylic acid in their liver. And of course, liver is where the highest concentrations of these terminal acids are proven to be found, including in polar bear, where we've looked at tissue distribution of these same compounds and found the liver to have the dominant concentrations. So these are very recent temporal trends of PFOS, perfluorohexane sulfonate, PFOA, and the C9 carboxylic acid, PFNA. And so you can see on the left, that's Western Hudson Bay trends, and on the right is Southern Hudson Bay trends. You can see the levels are higher in the Southern Hudson Bay bears, but you can see the trends going back. They're longer going back for Hudson Bay, but for both populations, you can see PFOS, for example, is not changing. There is some semblance of change in terms of annual half-life there for PFOS in the Southern Hudson Bay bears. And then when you look at the hexane sulfonic acid, you can see no change. Basically, maybe some small increase, in fact, per year in the last decade or so. And then you have the carboxylic acids, same sort of trend. So, meaning that high levels, particularly of PFOS, are the norm, and even up until now, where we've looked at samples collected even in 2019, we're still seeing that high, several thousands of part per billion of PFOS in bears from Hudson Bay. Of course, bioaccumulation, there is not a lot of examples in the Arctic showing actual measurements of bioaccumulation, except for a few, and here's one of them. This is a study we did. These are on polar bears from East Greenland, so more on the European side in the Arctic. But we looked at basically PFAs in the fat, blubber, and the liver of polar bears and ring seals from the same region, same time, kept all those variables as controlled as possible. But what we show here is actual accumulation, bioaccumulation, or biomagnification factor going from seal blubber to polar bear liver, or seal liver going to bear liver. And that's important because a lot of comparisons have been made in wildlife looking liver to liver. But in this case, polar bears basically do not eat ring seal liver, they eat ring seal blubber. So this is where we can actually measure values in both the bear liver fat and seal blubber and liver. You can see here we were able to generate a BMF. And the dark black bars are when we look at a particular PFAA in polar bear fat versus polar bear liver versus ring seal blubber. And you can see it makes a huge difference. And you can see, for example, on the right, we have the C9 to C13 carboxylic acids, which have hundreds, if not thousands, of BMF. And it decreases, although it does decrease with longer chain length. So clearly, values, BMFs that are in the thousands and higher, are really a serious bioaccumulation indicator, in this case from polar bears and their ring seal prey, because polar bears really consume mostly ring seal blubber. This is a very good comparison to a look at bioconcentration. So this is Arctic information I'm showing you, but this slide is true for any wildlife, that you have a lot of confounding factors in trying to get an idea of changes in time and space for PFAS in wildlife. So we're using bears here for an example. We can see that polar bears might eat a lot of ring seal, but they do eat a number of other species, and depending on the availability of those species, that is going to have an impact on ecological factors and what the bear is exposed to. And then, of course, an abiotic factor is climate change, and that is being shown to affect diet and food webs for polar bears. And then we also have the fact that the polar bear has a very efficient machinery for metabolizing anthropogenic compounds, including PFAS precursors. Again, limited amount of information, but they can completely convert the perfluorooctane sulfonamide to PFAS. So again, metabolism can also be contributing to those terminal acid concentrations and exposure in polar bear, for example. This slide really just kind of puts into context, this is PFAS, but this is contaminants in general in wildlife, that because they sit on the higher up on their food webs, that they tend to have a lot of other influences that will alter the exposure and fate of pollutants, including PFAS, in tissues in their blood, in their milk, what they pass on to their offspring. And in the case of the polar bear, you can see there's lots of other factors in terms of habitat degradation and change, biodiversity loss, and so forth. So this is part of the challenge in trying to understand compounds like PFAS in wildlife. So this is the last slide, and basically it gives you an overview of all the other types of PFAS that are coming online. You can see PFEX. You can see a number of other either a variation in terms of the hydrocarbon backbone, larger structures, more polymeric type structures, and you can see here we have a number of, this is just a small sampling, of course, of the replacements. There are many others. In fact, some numbers in the order of 4,000 or more different PFAS are actually in production. Information from the OECD. There have been a number of recent reviews that have talked about the breadth of PFAS and how little we know, not just in wildlife, but in the environment in general. So I give you these takeaway messages and this summary, and with that, I say thank you for your attention. And when we get to the actual discussion and period, then we can talk about this further. So thank you very much, and we'll talk to you soon. Bye-bye.